Well, good afternoon, everyone. Hope you guys all had a nice weekend. Um, Welcome to lecture 11. So today we're going to talk about viscosity and shear stress. I'm sure you're all excited because basically from here to the end of the course, the fluids are going to be moving. So yeah, I know. Much more exciting than hydrostatics. So hydrostatics are definitely important in terms of computing like pressure forces on solid objects that are like, for example, underwater. But the majority of fluids mechanical engineering moves. So that's why most engineering practice to deal with hydrostatics is usually civil engineering, but you might see that too in your engineering practice. But today is on viscosity and shear stress. So here's an example of honey being poured, and I think we all intuitively know that honey is a very viscous fluid. Today we're going to understand what viscosity actually is and how it's different between different types of fluids. Just a reminder of what we covered last lecture. Last lecture was on surface tension. So we characterized the force that what that tension force is. It's a gamma, which is a constant of our fluid times L. So L is the length that we cut. So if we cut a surface, an interface between a fluid or a fluid solid, we expose that force FST there. That force acts tangential to the surface at that cut. Since the force acts tangentially to the surface, if that surface is curved, there must be a pressure differential that will be able to balance the uncancelled portion of that surface tension force. We talked about contact angle, which is again a property of liquid. It's a property depending on the liquid and the solid itself. So this comes up in, for example, designing things that want to wet, say you want to beat off water, or things that want to absorb water. You'll worry a lot about contact angle. So if that contact angle there is greater than 90 degrees, that's the non-wetting. So that's where it kind of beads off the surface. If it's less than 90, then we call the fluid wetting. That wetting, non-wetting behavior leads to capillary rise in a tube. Well, you can compute the capillary rise using that equation there for H. We derive that equation by basically balancing the vertical component of that surface tension force at the tube interface with the weight of a certain column of fluid. So that's the reminder of all that we covered last lecture. Surface tension is generally a self-contained module in this course. So usually we won't worry about combined, say, surface tension and viscosity or surface tension and hydrostatics. It's kind of a self-contained force that we need to know about. But again, it only comes up at an interface between a fluid or fluid solid. And so usually we're just considered with one fluid. Context of today's lecture is, again, we're talking about forces in fluid motion. Today we're going to talk about friction force. So we're going to cover shear strain and viscosity and friction. So our learning objectives are to define shear strain rate in a fluid, to relate shear stress to this strain rate using viscosity, to compute the velocity profile and wall shear stress for a Couette flow. Couette flow is a very specific type of flow which we can use to study viscosity very carefully. So it's a very special case of flow, but as you'll see, it has a linear velocity profile, which is really nice for our analysis. And the last learning objective is about Newtonian and non-Newtonian fluids. So we'll explain what that means, and we'll be able to explain the difference between those two different types of fluids. So we'll go to the notes here. So we'll begin our discussion with shear strain rate. So I guess who can recall the definition of a fluid? How does a fluid respond to a shear stress? Any volunteers? This is back to lecture 1. So we said that a fluid does what under a shear stress? Yes, please? It forms continuously, so it keeps deforming. So in solids, we concern ourselves with the actual magnitude of that deformation because it's quite important. But in fluids, the magnitude of that deformation isn't really of interest because that magnitude will just keep going. It'll keep growing. So what we concern ourselves with in fluids is shear strain rate. So the rate of deformation. So since a fluid deforms continuously, continue, we care more about the shear strain rate rather than the shear strain magnitude. So let's define the shear strain rate. Say we have some sort of fluid element here. That we apply a shear stress to. This will look just a lot like it does when we're doing solid mechanics. So we apply shear stress to the top and bottom of this. We know that we'll experience some sort of shear deformation like this. And the angle at which these faces change, we'll call that d theta. And that's basically the shear strain. So in solid mechanics, you would have learned how to calculate that. In fluid mechanics, we're going to concern ourselves with the rate of change of that. So the way that we can strain a fluid element like this is through a velocity difference. I'll explain what I mean by that. So let's say at the bottom corner of this fluid element, we have some velocity u. And at the top corner of that fluid element, we have some velocity u plus du. So u plus du. The height of that fluid element is dy. So this length here, the green length, that only depends on the difference between the velocity at the bottom of this element and the top of this element. Since this element kind of moves in space, it's only the difference of velocity across that element that will produce that angular change. So the length of that is du times dt, where dt is the length of time over which the deformation occurs. So that du dt is just velocity times time. So we know that length is velocity times time. So the shear strain rate is just simply the rate of change of angle. So d theta dt. So how fast that angle is changing in time. We're going to use the geometry of this triangle here. So this triangle, to calculate that. So we have tan of d theta is du dt over dy. Just a reminder, the d's are just here to remind ourselves that this is on a very, very small scale. This is really just geometry and velocity and distance. So there isn't really anything special happening here yet with calculus. This is just the geometry of a small fluid element, and we're putting the d's in front of everything to just remind ourselves that it's small. Okay. So if we take an infinitesimal change, we get the tan d theta we'll just replace that with d theta. So even though theta can get quite big in a fluid, it can deform as long as we want. We're really more concerned with an infinitesimal change. So at an instant in time, how does the difference in velocity produce a difference in the rate of change of that angle? So this equation here becomes d theta by dt is du by dy. So the shear strain rate, the time rate of change of that angle, is equal to the spatial rate of change of velocity. So if there's a big velocity difference across that dy, so the top of this element experiences a much, much higher velocity than the bottom, then that angle will change quite fast in time. And the inverse is true for a small velocity difference. Are there any questions on that derivation? No? Okay. Now that we've defined shear strain rates, we can relate this to shear stress in a fluid using viscosity. So friction in a fluid. So when there is relative motion between parcels, which now there will be because our fluid is moving, when there's relative motion between parcels in a fluid, they pull on each other with a frictional force. And that's basically what viscosity is. It's how the parcels pull on each other. So you can think of that's what's happening sort of at an infinitesimal scale in the fluid. So when there are, or sorry, when there is relative motion, between parcels, they apply a frictional force to each other. So that frictional force is a shear force, just like how when you have something on an inclined ramp, I'm sure you're tired of seeing those problems at this point in your degree, but an inclined ramp, something's resting on it. The frictional force is kind of a shear. It's parallel to that surface. So that frictional force is a shear force. We're going to look now at Couette flow. So this is what Couette flow is. So we have the flat fixed wall on the bottom, and at the top we have another wall, but that wall is moving, so we'll call it a plate. So this is kind of a plate on the top. So that plate, say this is just like a plate resting on a big tub of water. That plate kind of moves along the surface of the water. And that plate, we know in order to pull something, that we'll need to pull it with a certain force. So that we'll just call that F. And the velocity that which that top plate is moving, we'll call that U plate. Find our coordinate system here. Okay, so we have this coordinate system. We're pulling the plate in the x direction, and there's a fluid in between these plates. So you remember from tutorial 1, we talked a little bit about the no slip condition. This is where it's going to come into play more. So at the bottom fixed wall, so the velocity of this wall is 0. Um, does someone know what the velocity of the fluid will be there based on the no slip condition? Also 0, right. And then how about at the top? So the velocity of the top plate is U plate. So if we assume the no slip applies there, what's the velocity up there? U plate. Nice. Okay. So our velocity looks something like this. If we assume a linear velocity variation, we get this. So the velocity varies linearly from 0 at the bottom all the way to U plate at the top of the plate. That linear variation is what the special case is. So that no slip always applies in a viscous fluid. It always sticks to the wall. But the linear variation of that profile is what's a very special case here for Couette flow. So the assumptions behind this, there's a long list of assumptions here. So we're going to take our velocity field to be only in the x direction. So the velocity field is some u I hat. There's no flow upwards. And we assume that this is kind of infinitely long. So there's no flow in the z direction, which in this case is in and out of the page. So the velocity is only, those lines are straight horizontal. There's no other velocity components. We take our no slip conditions, so u of y equals 0, 0, and u of y equals h is u plate. So here h is the vertical distance between these plates. We'll take a steady state laminar flow. So that means this is kind of a very slow, smooth flow. So we get this nice velocity variation. There's no fluctuations. There's no like turbulence being generated. We'll take partial v by partial x is 0. So that means fully developed. So x is the direction along the flow direction. So this profile doesn't change along x. Since partial v by partial x is 0, there's no change along x. Anywhere you look along the x-plane, you'll get the same linear velocity profile. We're also going to take a 0 pressure gradient along x. So the pressure gradient is 0, meaning that the pressure is the same at every point along x. So pressure, as we talked about, is quite important in a fluid, and most of the time pressure drives our flow. So in this case, we only have the only driving factor in this flow, say it's at rest, the only driving factor is the top plate that you're pulling on. So there's no pressure force being applied to this fluid. It's just the top plate. That's our only source of motion. It's our only source of energy. You can think of it that way. So only driving force is the top plate motion. So if all of these conditions are satisfied, you get that linear velocity profile that I drew there. And that profile is u of y with u plate y over h. So the assumptions on the right-hand side are required to get that nice linear velocity profile. This isn't something we're going to derive in fluids 1, but you'll derive this in fluids 2. So those assumptions will tell you basically what terms and what equations you can cancel and that sort of thing. So you get that linear velocity profile. So the slope of that profile is just u plate over h. Any questions on this? Any questions about any of the assumptions? I know those are maybe some new ones there. Yes, please, Aaron. Yep. The top plate would be h. You can think of it as also the distance between the plates. Any other questions? Yes? That's a really good question. So the question was, are we assuming that h is sufficiently large so we don't get a boundary layer there? Um, you'll learn more about that on Wednesday's class. This is actually assuming that h is quite small so that there's no boundary layer that forms. So this generally happens at very, very thin layers in fluid. You get this very special Couette flow. So that tells you roughly the scale you're dealing in. But if you don't understand what a boundary layer yet is, that's okay. We'll talk about that on Wednesday. Any other questions? Okay. So if we look at a fluid element along this profile, so I'm going to zoom in, I'm going to draw a box here. This red box is the, say, the fluid element we're going to look at. So that red box on the profile there, that one. So we're going to look now at that red box. This red box will experience the shear stress there. So that shear stress is tau. So far, we haven't actually seen how we calculate tau. But in, I believe it was Principia, so the Principia Mathematica, the Newton's very famous, I guess, calculus book, physics book, a very important book. Um, Newton hypothesized that shear stress is equal to some constant times the velocity gradient. So that's called Newton's hypothesis. And it tells us that the shear stress due to friction equals the viscosity times this term here, the du dy. We saw up above that du dy is d theta dt, which is our rate of strain. So the shear stress is the viscosity times the rate of strain of a fluid element. I'll define now what mu is. So mu there, that constant that determines the constant of proportionality here. So mu is called the dynamic viscosity. It is units of Pascal's seconds, which is equal, sometimes you'll see the units given as kilograms per meter second. You'll also see it given as the units poise, which are like sending the CGS system. So that's one poise is 0.1 Pascal seconds. But we'll generally use Pascal seconds in this course. This is just a very common unit used to define mu. So that's dynamic viscosity. So now we understand that under Newton's hypothesis, the viscosity tells us how much shear stress is created by a certain rate of change in a fluid. Are there any questions about Newton's hypothesis? Or maybe questions about dynamic viscosity? Yes, please.
We consider viscosity in the 2D and 3D cases.
That's a very good question. In this course, we're only going to do this case. So we only have variation in one, basically y coordinate here. In general, Newton's hypothesis isn't actually for this very simple case. It involves basically a rate of change tensor. So it's a matrix. So you get a 3 by 3 matrix if you were to do this in 3D. So I'm not sure, you might see that in fluids too. But you'll definitely at least see the 2D case in fluids too. So there's additional terms, but for now, all that we need to know is that there's a linear relationship between the rate of change and the shear stress for Newton's hypothesis. A good question. Any other questions? Okay. So let's look at what happens at the top plate up above. So let's look at a fluid parcel right along that top plate. So we're going to consider the fluid parcel that is basically by the no-slip condition. This red parcel here is glued to the top plate. So this top plate is moving. We're pulling it on with some force, and it moves at velocity at u plate. So at that, by the no-slip condition, the parcel sticks. I'm just going to clarify that this is at the top plate. So the parcels along the top plate are sticking to that top plate. So the fluid applies essentially a shear stress on that top plate, which is tau plate is F plate area. So this equation here, the shear stress on that fluid parcel at the top plate, we know that's still mu du dy by Newton's hypothesis. We also know that stress is force over area. So that force is applied over, say, the area of the top plate. We can calculate now the force it would take to drag a plate of certain area at a certain velocity. So this du dy plate, that's the velocity gradient, the du dy at the top plate. So for our linear velocity profile, that du dy is constant. So it's a constant slope. So for the linear profile, du dy is constant. So du dy plate is just du dy. You remember that du dy is also the slope, which is u plate over h. So now, if say we're given a moving plate and an area and a viscosity, we can calculate the force needed to do that. Are there any questions about that? So I will do an example here. So in this example, we're going to compute the shear stress. For Couette flow of water. We'll take the dynamic viscosity of water to be 8.9 times 10 to the negative 4 pascals times seconds. And then this second part of the question is what force is required to drive the plate if the plate area is 0.5 meters squared. So I'll give you a diagram here. So say that top plate, in this example, we're going to move that top plate at 1 meter per second. And say we have a small gap of 2 millimeters. If we assume this linear velocity profile, so we assume we have Couette flow, which I said in the question we do have Couette flow. We get tau is mu du dy. We're given mu. Du dy would be 1 minus 0 over 2 times 10 to the negative 3. So that du dy, so the 1 here is the velocity of the top plate. The 0 is the velocity at the bottom plate, which is 0 in this case. And the 2 is that 2 times 10 to the negative 3 is the 2 millimeters. So that's the height. So since it's linear, we can just do like change in velocity over change in height for du dy. That gives us a shear stress of 0.445 pascals. And the force on that plate is tau plate times the area. If we assume the linear velocity profile, we get a constant shear stress along that profile. So we get an F plate of 0.2 newtons. So I'm just going to review some of the concepts and assumptions here. So this is the core equation for a Newtonian fluid, is Newton's hypothesis. So tau is mu du dy. For co-wet flow, we have that linear profile. So du dy is a constant. So if mu is a constant and du dy is a constant, we get a constant shear stress anywhere along that profile of, in this example, zero point 0.4 pascals. At the top plate, the force on that top plate is generated by the shear stress of the fluid parcels sticking to that top plate times the area of the top plate. So here, tau plate, we assumed, since we have co-wet flow, we have a constant tau throughout our fluid. So tau plate is just tau. I will say that in general, tau plate isn't equal to tau. So for co-wet flow, tau is a constant, so we get a constant shear stress. Tau plate is generated by the velocity gradient at the wall. So let's say we have, I'll give a couple of examples of non-linear velocity profiles here. So let's consider the case where we have two walls, fixed walls, and we apply that pressure gradient. So this is a special case where U plate is 0 and partial P by partial X is greater than 0. So in this case, you'll derive this profile in fluids too. We actually get a parabolic velocity profile. Now, what creates the force on the walls, the drag force on the walls, is actually this slope, instantaneous slope at the wall. So du dy here I'm using wall and plate interchangeably. So tau wall is mu du dy. So that's like one special case where we get a different tau along this profile. So for example, at the center line of this profile, that du dy is 0. So there's no shear stress along the center line. But as soon as you start moving away from that, you start getting a shear stress in your fluid. And the shear stress in this case is highest at the wall where the velocity gradient is the highest. So almost always in practice, getting that du dy at the wall usually requires experiments or CFD, where CFD means computational fluid dynamics. So the reason we need that du dy at the wall is to compute tau wall. So the force to move something, speaking in very general terms, like the force to move something through a fluid, the fluid will stick at the surface of that something, and the force required to move that depends on the velocity gradient right at the surface of that something. So I would estimate that probably this is at least like this is billions of dollars a year that are spent trying to estimate near wall velocity gradients. So that's what like experiments, CFD, all that. So this is a general case here that I drew. So at a top plate where parcels stick to something. So getting that shear force at the wall is, I don't know, I did the calculation. So if it's say it's at least $1 billion a year spent trying to get the velocity gradient. So that means like in the course of this lecture, there's going to be tens of thousands, if not hundreds of thousands of dollars spent around the world. So this is what a very important quantity in aerodynamics. It's because the force required to move something through a fluid, the shear stress there is a very large component to that force a lot of the time. So accurately estimating that and predicting that tells you what force you need to drive the fluid. So for example, on an airplane wing, it's very thin, so there's a big area over which the shear stress will apply. So the dominant force of drag is this shear force. There are other forces on it, um, but like for example, I think it's a later problem, but it's related to this. The like some of the constants that you need later on to estimate this wall shear stress. I can't remember if it's the CEO or the someone very high, maybe the head of aerodynamics at Boeing has said that like the constants, if they're off by 5%, that's easily like billions of dollars that could be different. So this is a very important concept. For Couette flow, we get that special case of a linear profile, so that we know that du dy is a constant along that plate. But in general, du dy is a very difficult but very important property to estimate. So if all flows had that linear velocity profile, I don't know, as of a lot of fluids, people would be out of business basically. Um, Thankfully, real flows are quite complicated. Estimating that gradient is expensive but necessary. So let's talk now about Newtonian and non-Newtonian fluids. Actually, before I move on, are there any questions about that statements I just made, or shear stress and velocity gradients and viscosity? Okay. So let's talk about Newtonian versus Newtonian versus non-Newtonian fluids. Okay. So let's look at two example fluids here. So we're going to say we have a linear velocity profile here of water. So say we apply some shear stress to this water, tau, and it creates that linear velocity profile. If we have something that's quite viscous, like honey, it's kind of tough to actually estimate this viscosity, but say it's roughly 2 pascals times seconds. So it's thousands of times greater, the viscosity of honey, than water. So if we apply that same shear to both of these fluids, the velocity profile for honey, I've even exaggerated it there, will be much less steep. So if you have a big tub of water versus a big tub of honey and you have a plate and you pull at the same force, the honey will basically move a lot less because of this. So that's linear velocity profiles, which we get for a Newtonian fluid, aka one that satisfies Newton's hypothesis up above. So Newtonian fluids satisfy Newton's hypothesis. In fact, like the reason they're called Newtonian fluids is because they satisfy this Newton's hypothesis. So it sounds like a circular definition, but basically if it's a linear relation like the one we did above, that's called a Newtonian fluid. So non-Newtonian fluids, as you expect, non-Newtonian fluids do not. Okay, so I'll write tau is mu du dy, just to remind ourselves of what that is Newton's hypothesis. The general case is this. So you have tau is tau 0 plus mu du dy sum n. So in general, you get kind of this quadratic function, or this function that's to some power, like a power function. So the constants here That exponent n is greater than 1, we get it's called a shear thickening fluid. N is less than 1, we get shear thinning. And that tau 0, if that is greater than 0, we call our fluid a Bingham fluid. What tau 0 is it's an offset yield stress. I'll explain what this means kind of graphically in a second. So an offset yield stress. So this is the general case, just to be clear. So to get to Newton's hypothesis from the general case, we would get rid of tau 0, so we don't have that yield stress, and we say n is 1, then we get a linear relationship. If n is greater than 1, we get shear thickening. If n is less than 1, we get shear thinning. And what shear thickening and shear thinning means, there's a lot of different words for them, but this is the simplest. The shear thickening means as you apply the shear, the fluid feels thicker. So it's almost like the viscosity starts going up as you apply the shear. So the more shear force you apply to the fluid, it actually gets thicker. So you don't get a linear velocity profile. The shear thinning is the opposite. So when you apply shear to a fluid, the viscosity goes down. So a lot of fluids are shear thinning. For example, like ketchup in a bottle. Ketchup used to come in glass bottles. And so to get ketchup out of a glass bottle, you kind of bang on the bottle, and that's basically applying a shear stress to the ketchup. So ketchup is a shear thinning fluid. So it's quite viscous. If you just hold it upside down, the ketchup, I'll do a video as well at the end. The ketchup almost won't come out. But when you start banging on the bottle, you apply the shear stress and the fluid seems to thin, so it comes out more easily. So it behaves less viscous. The tau 0 greater than 0 is offset yield stress. So I'm going to do a plot to illustrate that one. Okay, so this plot is going to be the velocity gradient compared to the shear stress. So if we have a linear line, that's a Newtonian. A lot of fluids are non-Newtonian, but the two most common fluids in engineering of air and water, they're both usually Newtonian. A lot of this is a special case dependent thing, but air and water is safe to assume for most cases they're Newtonian. Shear thinning, we get something like that. So this is kind of curved. It's nonlinear due to that exponent n less than 1. Shear thickening is like this, so it's curved the other way. And that tau 0 looks something like this. So that is called a Bingham fluid. So I guess how you should interpret it is to think of applying a shear to a fluid and then increasing that shear you apply. And the output is the velocity profile. That's one way to think about this. So if you apply a certain shear, say we're dealing with a shear thinning fluid, if you apply a shear to that fluid and then a little more shear and more shear, you'll notice that it becomes easier to induce motion the more shear you apply. The opposite is true for shear thickening. So the Bingham fluid, that tau 0 is an offset yield stress, meaning that if you apply a shear stress to that fluid below tau 0, it actually doesn't yield at all. So it doesn't behave like a fluid at all. Because we know any fluid, the definition is that it deforms continuously. So if you have some sort of yield stress before it starts deforming continuously, it behaves like a solid. So a common example of this is like mayonnaise, like the low fat stuff. Like, you know how it's almost like solid, right? Like when it's just sitting there, you really have to like, so you take like a scoop of it and you kind of like hang it upside down, it might actually just stick. It might not. It behaves almost like a solid. It's only when you apply that offset yield stress that it starts to deform. So yes, please.
Egg whites use something similar because it like technically moves in one continuous like volume.
Yeah, egg whites are quite complicated, so I'm actually not sure about egg whites. Yes, Aaron?
Cornstarch and water be a shear thickening non-Newtonian fluid.
100%. Yeah, I'm going to show a video of cornstarch and water. That's a classic one. So again, the slope of the linear profile for the Newtonian fluid is mu. So that tells us the slope of that profile. So for example, honey and water will have different slopes. And you can compare this plot of stress versus strain to CF means compare solids. So remember you have like a stress strain plot, assuming some elastic deformation. Assuming you're in the elastic region, the slope of that line is the elastic modulus. So this is strain, but here this is strain rate. So this is kind of our equivalent stress strain plot for fluids. Again, a fluid deforms continuously under an applied shear, but how it deforms in terms of the strain rate depends on its characterization of either a Newtonian or a non-Newtonian fluid. Are there any questions about this? Okay, I'm just going to wait till everyone finishes. Yeah, so I'm going to show a short video now.
Not all liquids behave like this water, which pours exactly the same every single time. Some liquids change drastically depending on what we do to them. Go, Joe. Joe is running on top of a mixture of cornstarch and water. It's a liquid, but it acts like a solid when we apply
So this
force.
is a common thing, but the actual shear here is like the shear along the sides of his feet. That's where the fluid's actually being sheared, right? Because if you just say on top of it, that's like a normal. But the actual shear, it's thickening along the sides of his feet, which is holding him up.
To it. If Joe stops moving, he'll sink right in. Stop, Joe. That is an example of a shear thickening liquid because it gets thicker when we apply force to it.
So shear thickening fluids are actually pretty rare in engineering, but it does happen.
Kitchen, we deal with lots of shear thinning liquids, like these in front of me. I have mayonnaise, oyster sauce, mustard, hoisin, and ketchup. They go from a semi-solid to a liquid when we apply force. Well, let's check out this ketchup. When I turn the bottle upside down, nothing happens. When I tap on the side, it suddenly starts to flow. Because it changes based on outside force, you often end up with a lot
So
more
the shear
ketchup.
that's being applied on the ketchup is like as the ketchup's here, the bottle's here, as that kind of moving, the shear is being applied like at the surface of the bottle and transferred. So that's why it kind of slides along the surface of the bottle, but the bulk of the fluid, there's not that much shear motion in it. So that's why it kind of slides along the surface of the bottle when you're trying to shake something.
Bargain for. So if you've ever struggled to get ketchup out of a glass bottle, remember to tap gently and just wait for it to thin. On the other hand, if you ever find yourself in a vat of cornstarch and water, keep running.
All right, so are there any questions in closing about this? No? Okay, thanks everyone. I'll see you guys on Wednesday.